Deep rectangling for image stitching. A learning baseline. Although image stitching technology provides wider FOV, the stitched images suffer from irregular boundaries. To deal with them, one of the most common solutions is to crop the stitched image with a rectangle. However, cropping discards some image contents. Image completion can synthesize the missing regions. Nevertheless, they may generate some contents that seem to be harmonious but different from reality. To obtain a rectangular appearance without content increasing or decreasing, the rectangling technology is proposed. However, the existing methods heavily rely on handcrafted features such as line segments, making them fail in the scenes where the LSD algorithm fails. In this work, we propose the first learning-based rectangling baseline to address the above problem. There are two stages in the traditional rectangling pipeline. In the local warping stage, the seam carving algorithm and its inverse operation are used to get the initial mesh that best fits the irregular boundaries. In the global warping stage, an energy function is defined to optimize the target mesh. The rectangling results can be got by warping the input image from the initial mesh to the target mesh. In this work, we propose a compact one-stage pipeline for deep rectangling. Particularly, we define the target mesh to be rigid, and the only thing the neural network should do is to predict the initial mesh. In this manner, we convert the rectangling problem into a regression problem. Our goal is to design a simple baseline for deep rectangling. We concatenate the stitched image and its mask to form the input of the network. Then a feature extraction module and a regression module are designed to predict the initial mesh. However, this simple regression might yield uneven boundaries in the results. To solve it, we design a residual regression strategy to further predict the residual mesh deformation to smooth the boundaries. For the objective function, we design three terms. For the content term, we encourage the output to be close to the GT both at pixel level and semantic level. For the mesh term, we design intra-grid and inter-grid constraints to reduce warping distortions. In the former, we limit the size of a grid to avoid dramatic scaling. In the latter, we enforce the neighboring grids to transform consistently. For the boundary term, we leverage the mask to supervise the boundaries implicitly. Specifically, we warp the mask and constrain the warped mask to be close to an all-one matrix. We prepare our dataset in 3 steps. We first generate abundant rectangling functions by the traditional algorithm. Then we use the inverse warping of these functions to generate synthetic stitched images from real rectangular images. Finally, we remove the distorted samples manually. Here are several dataset samples. In total, we prepare 5,839 samples for training and 519 samples for testing. In experiments, we conduct quantitative comparisons, no reference blind image quality evaluation, and ablation studies. The proposed baseline quantitatively outperforms the traditional methods with a large margin. Then we display the qualitative comparisons in different scenes. The traditional algorithm fails in the regions where the LSD algorithm fails to detect the line segments, while ours succeeds because the learning-based solution can effectively perceive the nonlinear semantic features. Next, we evaluate our model in real image stitching applications. Our solution also produces more natural results even in these cross-dataset evaluations. Finally, we show some interesting applications of our rectangling. It can address the tilt problem together with rotation by warping the rotated image to a rectangle to correct the tilts. Also, it helps the downstream tasks. The irregular boundaries may decrease the detection accuracy for the objects near the boundaries, while rectangling helps to find the missing objects. That's all. Thanks for your watching.